Let's switch gears or talk about hopes. Eric,
Sure.
you go
Can
up next.
you go back one slide real quick? Whoa, this is kind of walking itself. Okay. Um, hey, I'm Eric Cady. I'm giving the talk on Hofus. Cover both the architecture side of things and our results summary. And I know it's my name on here, but I'm speaking for quite a few people who've done a lot of work to get Hofus working and to get it running in practice. And I'll call a few people out later. It took a lot of people to get this whole thing going. So, can we go to the next slide, please? All right. So I'm going to talk first about architecture. You know, what is Hofus? Why did we do it the way we did it? So Hofus, high order wavefront sensing and control. Brian already went and talked through Lofus. You can see it on here. That this is sort of doing the job of freezing the whole system in place. What Hofus is doing is the fine correction. It's correcting some of the mid to higher spatial frequencies that you see at the focal plane, and we're using our two deformable mirrors to do it. Um, Very specifically, it's sort of a two-part thing. We have one sort of algorithmic activity to measure electric fields. We do corrections based on the electric fields, amplitude and phase. Unfortunately, when you measure, you get intensity. So we have to do estimation there, and I'll talk a little bit about that in the next slide. Second part of is taking that information and turning it into something we can feed back to the DMs to do correction. And this is what we're using to dig our dark hole. Um, and so I have the requirement over here on the right side, TTR5 requirement. That's at level 1, the one thing we have to do. We went through a lot of work decomposing that into lower levels versus, there's a big error budget, this whole flux ratio noise structure that I'm not going to go into. I'm just going to kind of point at the the key numbers at the bottom. Uh, if we want to meet this and meet the allocations in the error budget, we want to be targeting the coherent part of the raw contrast, the part that we can actually touch with the DMs to be less than 5e minus 8, and the incoherent part to be less than 1e minus 7. And so these are all over 6 to 9 lambda over d, and we have goals that we would go into 3 lambda over d with the HLC, and ideally we'd like to be able to go all the way from 3 to 20 lambda over d. That's what we have the coronagraphic capability to do. And we have to do this in order to meet our contrast requirements. You can't do well enough by just saying we're going to line everything up really nice and we're going to get some nice optics. It will not get you to 5e minus 8. You have to do this sort of active correction with DMs to get there. So let's go to the next slide and I'll sort of talk through some of our algorithmic choices. So there are, floating out there are a few different ways to do wavefront estimation. The way that we use on CGI is pairwise probing. There's some historical reasons for that. It was developed for HCIT at JPL. We when we started doing the technology milestones for CGI back in 2014, we inherited all that. This was all being done in HCIT. So, and then historically we've continued to use it because one, well, it works. Two, there's a real benefit to saying, well, we showed that it could work. Why would you switch to something where you're losing that testing heritage? So that's kind of led to this. Not saying there's the only one. There's for people thinking about the future. There's been comparisons, recent comparisons even. There's one in Jada's last month on pairwise probing to something like the self-coherent camera or implicit EFC. They're all very effective ways of doing the same thing. And what that something is trying to take a bunch of intensity images, which is what you're getting out of your camera, and trying to back out a complex image plane electric field out of this. And this is complicated because it's not just the intensity from the starlight you're getting there. You're also getting all the other background intensities, some of which are astrophysical, and that's your planet, for example, where you can't correct your planet. Zodi, exozodi, stray light, ghosts, like they're not all external to CGI effects here. And so model-wise, we say there's some, coherent intensity and some incoherent intensity. that was what we're seeing in any particular images. And so what we do here is we use a series of what we call probes. They're small DM settings in the pupil, and we use them. We just apply them one at a time. Put on the DM setting, take an image. Put on the next DM setting, take an image. And we'll use pairs, one of which are the same relative setting, just positive and negative. Take the DM delta and multiply it by -1. Um, and this simplifies probe amplitude estimation. It's also got some fuzzier benefits in terms of DM creep that you're putting on the same thing. You're kind of balancing what you put on. But it's primarily the probe amplitude is the most useful piece. You can actually see here at the right, these are 3 examples of the probe shapes that we used. These were a set of probes that we used during TVAC for use with the narrow field of view architecture. You can see that top ones is this sort of coast. They tend to be sync sine type shapes, or sine is some kind of sinusoid, so the cosine, and then 2 sines in different directions. And those provide modulation all the way around in 360-degree around the dark hole. And that's going to amplitude. Phase we get from the optical model. I'll talk about optical model a little bit in a couple slides, but I know AJ also spoke a bit about this. And we need at least 5 images. Turns out you go through the math. There's, especially if you're trying to include your incoherent light, there's 5 unknowns. So okay, you need 5 images. We use 7. It helps avoid some issues with poorly conditioned solves. Also, just there's some areas, particularly with these, you see it right, the sinusoidal ones, those will modulate some areas, but they have these null regions. And so by using more probes, we try to avoid having areas of the focal plane in the dark hole that we just are not modulating much at all. And then at the end, we back up the incoherent intensity by subtracting the coherent intensity. I'll call out something here that you can see that how well we know our incoherent versus our coherent is basically a quality of how well our wavefront estimations work. So we're not walking in here with a ground truth on what's coherent and what's incoherent, even though you did see requirement numbers on those earlier. I'll return to this a bit later. Next slide, please. So this is all nice. You got some electric fields. What are you going to do with them? We use an algorithm called electric field conjugation to do the correction. It's a fancy least square solve. So we model the field in the local vicinity of whatever your electric field is as some measured electric field plus size of motions from your DM and the effect of change in the electric field as each actuator in the DM is moved. I think this is probably familiar to many of you as being called the Jacobian, and that'll probably come up a few times in the subsequent slides. And so when you have these things, you can say, okay, well, locally, if you make a move, you're going to create some electric field, and we want to select that set of DM moves such that it minimizes the electric field residual, conjugates existing electric field. That is where the naming come from. And so in practice, you can break this down into sort of an AX equals B solve equation. And this is something that you can solve with just super standard linear algebra tools. I think we have 3 of them that we implemented for CGI just as cross checks, and it worked fine. What we do for CGI is we kind of push this a little further. So we do our electric fields. We do use weightings on both electric field and the DM side. On the electric field side, if you can use this on pixels, you can deweight them to 0. You can say they're dead, or you want to remove them for other reasons, like say your estimation was kind of garbage. We can also apply extra weightings to them, and we want to do that in cases where there's areas of the focal plane region we particularly want to target. I know June could tell you could probably talk to him at a later break about this, that during the milestone testing, he used it a lot. He used this a lot with HLC testing, back in 2015, 2016, to emphasize that 3 lambda over d region to really focus the control at getting better near the inner working angle. So that's something that you're capable of doing with this uh, way of doing the control. Similarly, we do these things on a DM. We use it to capture dead actuators, tied actuators. We have both of those things. Um, and I will say the tied actuators are actually intentional. We put in a lot of CGI has a lot of tied actuators in the corners and the center region, which saves us a lot of mass and power on our DM electronics. So that's actually a good thing. We just need to take it into account. We do chromatic control. When we collect data with different subfilters in CFAM, the color filter alignment mechanism, that are, say, 3% bands, 3 to 4% bands, covering a 10% band. And so then you get this way you get some chromatic variation while you're doing your control, and allow you to correct these chromatic speckles. And that's important as you get to higher contrasts. And so we can include that in our electric field. And finally, in this, I kind of don't want to understate this one, we can add a regularization term. And this balances how much the least square solve is emphasizing sort of model versus data. And this is actually really, really important. Like I can't understate how, like, this is something we learned in the process of doing CGI, just how important this is. That we do, or a term we've been calling regularization scheduling or beta bumping, beta scheduling, um, to change this regularization term as a function of iteration. And what happens is you go to very aggressive regularizations. You correct these terms that require a lot of DM motion without making a lot of change. These sort of funny amplitude and chromatic modes that are basically impossible to get otherwise. And then you go to a less aggressive regularization, and it can't touch those modes. It just cleans up anything that was left over from model mismatch. And so when we sort of walk through some of the contrast curves in a few slides, you'll see this beta bumping, where things get briefly worse before they get better. And this is intentional. This is part of the way we end up at higher contrast. And you can look at a few papers we wrote after the milestone testing, saying, hey, this is what we need to do and why. I'll call it David Marks's paper at the end in particular as a very useful one. So the last thing we do that's sort of specific to our wavefront control, and maybe has not been overly publicized previously, is we minimize the intensity relative to the peak of the PSF, the normalized intensity, rather than just intensity. And the reason is we want to keep the PSF sharp. You can imagine the wavefront controller saying, hey, what if I smear everything out? Guess that really makes a very dark hole. Well, yes, it does, but it gets rid of the planet, which is not what we wanted to do. So next slide, please. Last thing, I'll touch a little bit on the optical model. I know AJ did talk a little bit about this, so I'm not going to go too deep on this. But we use an optical model a lot in HOFUS. We're doing a probe phases with it. We're doing Jacobian calculations with it. We're doing all the sort of outer structure stuff with this, like what contrast are we at this iteration? What are we do next iteration? These all use the model to do these estimates. And so we do rely on it quite a bit. And AJ talked about the tools and the ground software that we use to do this. And I'll just say this now, like if your HOFUS is stopping somewhere in the middle at some moderate contrast, that usually speaks to model mismatch. So actually, I think it was really a really nice thing that we didn't see this happening so much in TVAC. It really speaks to the efforts we made in doing the calibration really paid off. So next slide, please. So I've talked about HOFUS. I haven't gone so much about GITL. GITL, ground in the loop, is how we actually implement the HOFUS. And there's some history here. So up till about 2019, we've been planning to do this all flight software, all flight software all the time. We actually had 2 pieces of hardware in the plan that were entirely dedicated to nothing but HOFUS. There's a processing board that would do computations, particularly Jacobian computations, which were taking tens of hours, if not, north of 100, just because of the limitations of the hardware that was space qualified at the time. And then, and we did other things on there too, some of this calibration stuff that was talked about previously. And we had a dedicated solid state recorder. And this was to store those Jacobians, at least partly due to because we didn't have any other non-volatile storage that big, and no one wanted to risk, hey, something happened, there was a blip, we just lost 70 hours of computation, or even, see, we wanted to reuse one that we used previously the last time we were observing. Well, I hope it stuck around for a few weeks. Uh, so we ended up with this extra hardware, a lot of flight software work. It was, a very complicated implementation. We were doing, had an active work on FPGA acceleration of the model calculations. And about October 2019, we had the mission PDR, and they raised some red flags saying, this is a real schedule risk for flight software. I mean, there's schedule risk, a lot of things, but particularly HOFUS. There was also concerns about mass power. It was somebody, I'm actually not sure who on the Associated Tiger team suggested the GITL. We looked at it, we said, yeah, this could work. And we worked out a way to do this that splits the processing that's needs to happen for HOFUS between the flight and the ground. So what we do on board is we go and we collect the data. We would have done this anyway. We would do it with just the sequence engine on board. But then within the CGI flight software, there's a processor that does a sort of same thing as the ground pipeline. It is sort of a thinner level. It doesn't do some of the more detailed corrections, but it gets it to a level where it's been dark subtracted, flat field corrected, bias subtracted, and takes all the images that you took at a particular filter, sub-filter setting and DM setting. It combines them all together and it crops them down to just a little window around the dark hole. And this is a really key element for data volume, because we have to go up and down through the S-band pipe, which is orders of magnitude smaller than the channel that you can use for dropping science data down. And it's the only way to get anything back up. So that's the amount we left on board, and everything else we moved to the ground. All estimation, all control, all sort of in side stuff like what camera settings do we want to use for next time? What do our metrics look like? Everything's on the ground. And while we were there, we also kicked all of the calibration stuff, all the alignment stuff, everything we could kick off. The spacecraft we did. The exceptions were the speckle balance, as you heard about earlier. There wasn't a way to do that in a ground loop manner. That was really about it for this. We kicked everything else out, and while we were there, we descoped those two pieces of hardware, and this, turned out to work great. We reduced our mass, reduced our power, reduced our software complexity, reduced our verification challenges. I'll be frank and say it. There's a very real chance we might not have been able to finish on time if we hadn't done this 5 years ago. And in ground software, it was simpler, more effective. You could there was an ongoing challenge in the flight software implementation, is that the set of people that really know how to write flight software, which is a very specialized skill set, and Kylie will talk about it in day 2 tomorrow. It's sort of disjoint from the set of people that have been doing coronagraph experiments in the HCIT, and so we worked out this sort of transfer and port scheme to get the data over, but it wasn't like there was one person who's like, I'm going to write a HOFUS thing in C++ or VxWorks and Scratch. The person didn't exist. And then all the issues, the timing and the computation, the storage, it just disappears. You buy another server. It's a drop in the bucket on the scale of a space mission. Piece of cake. So GITL has worked out really well for us. And could I get the next slide, please? And this is just kind of an overview at a high level of how GITL works in the overall Roman system. So for any given iteration, CGI takes images, it processes them, it's running out of the sequence engine. And how long this takes, really varies. As you get to deeper and deeper contrast, you're taking longer and longer exposures to get the SNR you need to do the correction. So that's time varying. Once you get to there, it's a little more predictable once you get to the rest of it. So we're taking these images, we send them to the housekeeping recorder. This is actually going on as you take the image. You take them, you ship them out, take them, you ship them out. There's some parallelism here. And then these go down via S-band to the ground station. They're relayed to the Mission Ops Center, the mock forwards on to Science Support Center. That's SSC, where you all are sitting right now. And SSC will take the raw packets, turns them into the inputs to HOFUS. Then there's a JPL piece of the ground system, the CTC, that delivered, sort of a black box HOFUS. Inputs come in, those images come in, and the other data packets that were sent down, and DM settings and camera settings for the next iteration come out. And that black box, it takes by requirement no more than 60 seconds to run. And then with those outputs, SSC prepares them into commands. They're sent up, they're run. And this is preparing, new DM settings to run on the next iteration, preparing the cameras, setting them in flight software parameters. And this whole loop is expected to take less than 30 minutes. The last CBEs I was seeing 20 odd somethings. It's I don't think it's been updated more recently than that. So now just note for the record, if you go to the next slide, what we did for INT was cut almost everything out of the loop, because all of those ground system elements are not ready to do this yet, and just had the IINT ground system sitting in for both the spacecraft and the ground side of things. And then SSC did use their algorithms. They were just at JPL, letting us do this sort of ground in the loop approach, but with not physically, going back and forth to SSC. But I think the key point here is still valid. The technically relevant pieces, not so much the piping, were still used when we were doing this in TVAC, and that was one of the key things we did want to test and make sure we're working as expected. And could I get the next slide, please? All right, so I walked you through the architecture. Here is, I think, moment many of you have been waiting for. This is how HOFUS did. So we ended up, over the course of several shifts, over 30 shifts, from a lot of people, many who you've seen today or we'll see tomorrow. We did manage to get good dark holes in with two different coronagraph architectures. On the left is the band 1 narrow field of view with the HLC mask. This one makes a dark hole from 3 to 9 lambda over D. We only need 3 to 6 by requirement. But this has been sort of our baseline, but we did, you can see some numbers up there too for how it did over the entire dark hole. We also had some time available and took advantage of it to do some band 1 wide field of view masks. These were contributed masks, but for various reasons it was convenient to stay in band 1 and test something, because as it turns out, the band 1 wide field of view mask also technically meets TTR5 in that it provides a dark hole over 6 to 9, 6 to 20 really. And so we did both. And actually you can see in the numbers at the bottom, we managed to push both of them down in the 6 to 9, down below the requirement levels for both coherent and incoherent contrast. And actually, excuse me, we pushed a little harder, in that because of sort of the ambiguities in the wavefront estimation, that there's no ground truth for an incoherent intensity. What we ended up doing was targeting the smaller of these two requirements to be larger than the total intensity. And you see actually, you add these up in your head, that yes, both of these ended up less than 5 times 10 to the minus 8, sort of regardless of whether we got the coherent incoherent split right or not. So both of these performed suitable to do TTR5 with either architecture. Next slide, please. This one has a movie on it. Is it? Are you able to get the movie running?
We'll do it for you.
Okay, thank you. So yeah, these are movies that June put together, which should cannot play media. Well, that's lovely. If you give it a minute, I might be able to show it on my end. Give me a second here. I'm gonna take over the screen sharing for just a second, if that's okay.
Okay, go ahead.
Okay, so I think let's see if this works for me.
You can see your screen now.
Okay. Okay. So what's happening here? This is June. There was mention, in previous talks of multiple runs. Particularly, there were some centration issues that AJ talked a bit about. So this was sort of the third run. We went down and we did some restarts and so on. And finally, we did a clean start to fix the centration issues. And so this was just one straight run we did, and it went great. You could see the beta bumps as we went along. As it goes up, you could see the contrast spiking a little bit and going back down. And then we did a little bit more aggressive to try and get some of the finer speckles. Then a little bit less aggressive at the end as we're coming to the end of the available time. And so this was the HLC, and there's sort of two things limited. We were limited by time available. You can see the sort of slow roll at the end. That was us, trying to wrap things up cleanly, without having it spike up and end at like halfway through right here. And then the other part was I'm not sure how much has been discussed previously. There was an incoherent light leak that was creating some stray light. We post TVAC, we ended up fixing this with a baffle, but it does pose a little bit of an incoherent floor on this guy. But the takeaway you should say is that doesn't seem these floors appear to be primarily, there's the stray light one that we fixed, and the other one is a logistical issue. There doesn't seem to be an inherent floor that we found yet in in the speckles here. So this represents a good performance. I don't think it necessarily represents the final performance that CGI is capable of in this mode. And I'll jump over to this is the there we go. And here is the wide field of view one. You can see a similar thing. This is run over a larger region out to 20 lambda over d, so you can see the circles on there again. Excuse me. And yeah, this one was a bit of a target of opportunity. We had some extra time available, and we took advantage of it. And we were, I think, relatively limited by that, logistical structure. You can see that when we get down to the end here, it's still going down. If more time was available, I don't see any particular reason why this represents a fundamental flaw in performance. And this one, and as I said, this one was based around a shape pupil chronograph architecture. So these are the two chronograph architectures that are being supported. And I think I could just run this for the last two slides. I think that's almost done. Let's see. So some open issues. Stellar centration. I think I'm running a little long here. AJ talked about this. So it was a bit of an issue and lesson learned. We came out of that. One other thing we found is that during some of the nulling runs, we found we need to swap our DM probes. Um, Not even really the shapes of them, but where they were centered in the pupil. And this is something we hadn't seen before, in any of the technology maturation tests or any of the models. And so we're still not quite sure what was causing it. So this is sort of an open issue that we'd like to understand why we had to do that. Um, and one piece I'll mention, and nice to have, especially for these sort of requirement type questions, if if people are looking for something to do, it would be nice to have some increased confidence in how much it's split between coherent and incoherent light. Um, I mean, for CGI certainly, but I think with eyes towards HWO, where the incoherent light requirements are likely to be quite a bit looser. So understanding what's actually incoherent might be helpful from a verification and design perspective. Um, so let me just jump to the summary. I think the key takeaways: we got better than TTR for 5 performance with 2 independent chronograph architectures. They went 3 to 9 and 6 to 20 lambda over D between them, and both of them did a 360-degree dark hole to do that. And we don't After TVAC, we really don't fully know the CGI contrast floor. In all these cases, I think we're limited by available time rather than any particular systematic that we've identified in the system. And this all worked together the first time. Like we just went and did it. And so I think there was a like I can't really understate like how great this was. And I think this is a real benefit that we did a lot of tech maturation. We pulled these things forward. These things had high heritage at the point we were using them, and we did a lot of unit testing and functional testing and just advanced work, including testing to writing requirement structures around them and verifying those requirements, to make us believe that the things we wrote would work, and they did, and it really did pay off. Um, and I think I'll just add the last, which I think is equally important. This is the best tested you fly configuration available to us. You collected the data, on board. We're running the GITL stuff on the ground. Air quotes there, sure. Um, but in the absence of the rest of the ground system, which is not quite prepared to do this, this is as close as we can get to doing GITL in the way we intend to do it. And actually, I'll just mention that we will do at the Roman level, we will do end-to-end information systems testing with GITL at the observatory level with the entire ground system in the loop. And so this loop of things going around will be tested. The only thing that's different perhaps is that the observatory level there's no stimulus, there's no CVS, so we can't do real coronography in real time. So SSC will be doing an injection where they'll be injecting in TVAC data that we'll be using to close the loop. But other than that, it's we're going to do it exactly like we're going to fly it. So I actually have no idea how late I am. Are there questions?
Thank you, Eric, for calling in, recovering from illness. I want to add that the GITL actually concept was chanted by Lee Feinberg right after PER. It is. Thank you, Lee.
I'm glad it worked because I know I would have been blamed if it didn't.
It's one of the trade recommend for Hat World too. I've got a question here. We're going to run late here. I think there are a few people planned meeting 3, and that's delayed to 3:30. So we'll want to make sure we pass as much information possible to the audience here. So, question, yes.
Hey, Eric, I'm wondering if the time it took to dig that dark hole is mappable to how long it'll take on Sky for a, via 5 target or something?
We've done some preliminary mapping. Excuse me. We have in the form of timing budgets, at least at the commissioning level. It's not quite a a one-to-one map. We actually expect, it's weird to say, but I expect commissioning to be a little better because we have something of a starting point to use from the ground testing. But I think we're talking the same comparable. I have to get back to you with a more precise timing, but we do have the capability to give you to identify that number right now.
Okay, thank you.